Thanks for the introduction. I'm Nikan from Xi'an Jiaotong University. Today, I'm going to talk about faster mining concise access control intents on public cloud. This is a joint work of Xi'an Jiaotong University and Huawei. Nowadays, more and more software applications are increasingly deployed in the cloud. To secure these applications, major cloud providers such as Amazon, Google, and Huawei offer identity and access management system, that is IAM, and IAM play a crucial role in cloud security. So what is IAM? IAM systems operate under a shared responsibility model. Cloud customers protect their resources by specifying access control policies using JSON-based policy languages. The cloud provider engine then determines whether each access request is authorized according to these policies. Unfortunately, data breaches caused by misconfigured access control policies are alarming common. Numerous incidents reported in the media highlight this issue. For example, a misconfigured Amazon S3 bucket exposed the personal information of more than 50,000 Australian employees. These breaches can result in substantial economic losses. For instance, the Capital One data breaches led to an 80 million regulatory fine and 190 million class action settlement. Why are IAM policies so error-prone? Actually, even though cloud providers offer policy templates, cloud customers still need to write and customize IAM policies themselves. The main reason is their complexity. Let's take a simple IAM policy as an example. First, IAM policies support wildcard semantics. For example, the pattern department1 user txt matches any file in the department1 dictionary whose name starts with user and ends with txt. Boolean semantics also exist in IAM policies. Within the same domain, multiple values represent an OR relationship. Across different domains, the relationship is AND. Furthermore, negation can be expressed by adding not before a domain. With wildcard and Boolean semantics, it becomes difficult to determine which requests are permitted by a policy. Let's take the two requests in the bottom right corner as an example. Even for the simple request, it is non-trivial to determine whether they will be allowed or denied. The company sales group also provided a report supporting this finding. According to the report, 51% of cloud data breaches are caused by misconfiguration or human error. Therefore, many tools have been proposed to assist users in reducing policy misconfigurations. The first category of approaches focuses on checking equivalence or public access, such as Zelkova and Ambit. However, these approaches require manually defining an ideal policy or public principle. The ideal policy itself still requires users to fully understand the access requirements, which may also introduce errors. The second category focuses on quantifying allowed requests, such as query. However, this approach requires prior knowledge of the number of allowed requests. For example, how can we understand whether the number of allowed requests is 2 to the power of 104? Another approach is mining access control intents to secure policy by helping users better understand their policies. Let's see a concrete example. Suppose a company deploys its business on the cloud. It has 2 departments and 3 employees. The administrator defines the IAM policies on the left to control employees' permissions. Recall that these policies are hard to understand. It is difficult to determine who can perform which actions on which resources. However, with a compact set of declarative statements that is access control intents, we can easily understand who can perform which actions on which resources. From intent 1, we know that employee 1 can access the resources in department 2. From intent 2, we know that employees 2 can access the resources in department 1. Meanwhile, employee 3 have no permission to access any resources. But the state-of-the-art method, that is AWS Access Analyzer, suffers from low scalability and readability. It adopts a staged refinement process based on predefined levels. We illustrate this limitation with the example on the right. Access Analyzer iteratively checks the following constraint. Specifically, it subtracts all child intents from the counter intents, and then checks whether the remaining intents has any intersection with the policy. If the constraint is unsatisfiable, it refines this policy and all its child intents are added into the work list. For example, after subtracting as child intents, intent 1 have no intersection with the policy. Then Access Analyzer refines it and checks its child intents again. If the constraint is satisfiable, the intent is included in the final set of intents. So intent 6 to intent 9, these 4 intents is the final intents. In summary, the entire solving process requires 9 rounds of SMT solving. The final number of generated intents is 4. However, we only need intent 6 and intent 9 because all other intents are covered by these 2 intents. We further analyze another policy with only 15 statements. The number of SMT solving rounds exceeds 1,000, and each SMT solving instance is complex. These reasons make the mining time exceed 1 hour. Besides, the number of generated intents reaches to 125, which is 10 times larger than the number of statements in the original policy. So, can we mine access control intents within a reasonable time while maintaining conciseness? We therefore propose AccessRefinery, which takes an access control policy, that is IAM policy, as input and produces the corresponding set of intents. It consists of 3 modules. Here we keep the logic of AWS Access Analyzer unchanged at the module of the intent miner, and we design a new module called intent reducer to remove unnecessary intents from the output of intent miner. We also design a new data structure, MCP, which decouples the underlying Boolean operations from the higher level application logic, and then accelerate multi-round SMT solving. It abstracts low-level operations and allow upper layer algorithm to focus solely on their own logic. Moreover, AccessRefinery is fully automatic and requires no manual intervention. We next introduce multi-round constraint preprocessor. Before introducing MCP, let me briefly explain how an SMT solver works. First, the SMT constraint is translated into Boolean formula in conjunctive normal form. The resulting formula is then passed to an SMT to a set solver. If the set solver finds a satisfying assignment, the assignment is further checked by the corresponding theory solver. If the theory solver also reports satisfiable, a valid solution has been found. Otherwise, the solver backtracks and searches for another assignment. This process continues until a theory satisfying assignment is found, or the constraint is proven unsatisfiable. It works well for single-round SMT solving instance. However, in multi-round SMT solving, the theory solver is repeatedly invoked across different rounds, leading to substantial redundant computation. Therefore, we ask, can we reduce this redundancy? We therefore propose the multi-round constraint preprocessing MCP to avoid repeated theory solving across multiple SMT solving rounds. MCP is based on the idea of equivalence classes. We observe that in access control intent mining, all possible values are known in advance. We refer to these values as labels. Since all labels are known before solving the SMT constraints, the differences between solving rounds lies only in how these labels are combined. Therefore, MCP pre-partitions the labels into disjoint regions, namely equivalence classes. For example, the resource domain can be partitioned into 4 disjoint regions, while the IP address domain can be partitioned into 3 disjoint regions. Values within the same region always yield the same satisfiability result for the theory solver. Then we can map each label to its corresponding equivalence classes before solving, avoiding repeated theory analysis. We can see from the right figure that these three string labels can be converted into an integer set. Pre-computing of equivalence classes is performed only once, and the results are stored in the mapping. We next show a detailed example how we use this mapping to solve an SMT problem. With the mapping, we could easily convert the label appearing in each domain. Then we can assign a corresponding position to each domain and map each equivalence classes to a unique bit vector. Then, based on the semantics of IM statement, we can encode each statement into a bit vector. We can further combine these encoded statements to represent the entire policy. As a result, the operations between policies and intents are transformed into operations between bit vectors. This raises another practical question. How can we efficiently perform operations on these bit vectors? Although we could use an set solver, we chose to use BDD. With BDD, we can support incremental computations because it allows more efficient reuse of intermediate results. A BDD is a directed acyclic graph consisting of terminal nodes true and false and their variable nodes. The path from the root node to the true terminal node represents a satisfying assignment. To this end, we design MCP as a general data structure, which can also benefit either studies. MCP supports different types of values and hides the underlying implementation details. Specifically, MCP adopts a two-layer architecture and supports multiple types of values, including regex, bit vector, range, and enumeration. We open sourced MCP and hope that it can be applied to other research domains as well. We give a simple example to show how to use MCP. Suppose we want to check whether the negation of intent fix has an intersection with a policy. First, we use the add-value function of MCP to initialize MCP. Then, we invoke the partition ACS function to partition equivalence classes. This operation only needs to be performed once. Then we use the getValue function to acquire the BDD representation for each label. Next, we use Java chain calls to encode the Boolean logic among statements. Finally, we encode the policy and intent based on the Boolean logic. Then we can easily determine whether the intersection between negation of intent fix and the policy is satisfiable. During this process, we also found that after partitioning the equivalence classes, we can flexibly combine these values for Boolean reasoning. We next introduce intent reducer to reduce the redundant intents. After mining the intents, we aim to remove redundant intents while ensuring that the remaining intents still cover the original policy. This naturally leads to a minimum set cover problem. However, both policies and the intent represent infinite spaces. Therefore, how can we solve the minimum set cover problem or an infinite space? We employ equivalence class techniques to transform the min set cover problem over infinite sets into an equivalent problem over finite sets. The partitioning of intents and policies into equivalence classes can be efficiently performed using our MCP. We want to highlight that the ACs are defined at the policy and intent level, while the MCP focuses on partitioning underlying values to accelerate Boolean computation. Finally, we select intent 6 and intent 9 as the minimum number of intents that cover the entire policy, thereby reducing redundant intents. Moreover, since each policy and intents map to only a small number of ECs, we can solve the min set cover problem exactly using IMP solver. In our evaluation, we evaluate our approach on 3 types of policies. For implementation, we open source both AccessRefinery and our implementation of AWS Access Analyzer. All code is publicly available. Next, we conduct a series of basic Boolean operation tests to show the correctness of MCP. Moreover, we compile the intents generated by AccessRefinery, our reproducer Access Analyzer, and the AWS Access Analyzers through the CLI API. They produce the same results with the further validate the correctness of intent miner. For the correctness of intent reducer, please see our paper. For readability, the results show that our intent reducer reduces the number of intents by up to one order of magnitude on both real and synthetic datasets. Moreover, the reduction becomes more significant as the number of allowed statements increases. We next show the results for scalability on synthetic datasets. For fair comparison, we use the SMT solvers, these 3, and the specific file as baselines. For intent mining, AccessRefinery achieves a speed up of 2 to 2 orders of magnitude. For intent reduction, AccessRefinery achieves a speed up of 1 to 4 orders of magnitude. The reason that intent reducer achieves the better speed up for intent mining is that intent reduction requires more rounds of SMT solving. On real-world datasets, AccessRefinery achieves up to 15 times speed up in intent mining and up to 170 times speed up in intent reduction. Next, we conduct a micro-benchmark experiment. The results show that with a small pre-processing overhead, MCP enables AccessRefinery to reduce the time of single-run SMT solving from seconds to milliseconds. Finally, we summarize. In this talk, we show that access control intents are essential in the cloud environment, but mining them suffers from low scalability and readability. We therefore propose AccessRefinery, which achieves 1 to 2 orders of magnitude speed up in intent mining and reduces the number of intents by up to 1 order of magnitude. Thanks for the listening, and I'm happy to take any questions.